So you have some data or vector or scalar, but multiple data points, and you have some parameter theta. And theta is unknown, but it is not random. So you make all these wireless measurements. Usually your parameter is just unknown, generally, right? And but path loss, this and that, there could be the random component. So then you go back to the previous things that we discussed, random parameter estimation. And but nevertheless, I want to tell you that in the design of experiments, you will design the experiment such that the data has something to do with the parameter. You will not be collecting data which has nothing to do with the parameter. So I'm going to, and this is generally because of the noise and this and that, the data is random. So we are going to assume that, I'll generally write it like this, and the short form notation may be just this. So by this comma, I mean these are the random variables, but these random variables also depend on this unknown. This is unknown to us. But the random variable is a function of theta. That this joint density function is a function of theta. But it's not like the, for example, in a Gaussian random variable, the mean and variance may be unknown. They are not random variables, they are just mean. If they are unknown, then you have two parameters which are unknown there. In the Poisson, you know something is Poisson. So Poisson has one parameter, lambda. But if you don't know the value, then it's unknown to you. There is nothing random about it, it's just unknown. So if you say, sometimes, this is also written like this, etc. I don't like to, I just use column just to show that these are the random variables, but it's also, theta is also present in the joint density function. So if you say, since we have studied the minimum mean squared, etc., let me look at the conditional density function of, the expected value of theta given R. So that's going to be theta, by definition, multiplied by the density function of theta R1, etc., Rn. But remember, in this case, the theta is just unknown. Whatever you do have the joint density function, right, of the data. And so if I pull out the theta, remember theta is not a random variable, so it will be area under the density function. So if you use this approach, you can come up with this meaningless result, because this is what you are trying to estimate. And moreover, here we should be substituting the posterior density function of theta given the thing, but all we have is this. And so if you use this, it's going to come out that the minimum mean square estimator is simply theta itself. So that's like catch-22. It's not getting us anywhere, right? So any of the previous techniques that we have used here will not be applicable simply because theta is not a random variable. So this is where the principle of maximum likelihood comes up, is the one which is used universally. So this is by Fisher, I think, the statistician, English statistician from the last century. So the idea is that here, remember, theta is unknown, so this is not going to be meaningful. So all we have is this. All we have is the joint density function. Because of the observations, we have the joint density function. And if you look at here, the observations have been collected. So these are all known, and this is the only unknown. If you look at here, this is the only unknown. So you could plot this if you want as a function of theta. this joint density function R1, etc., Rn and theta. Usually you also write this in this form. Saying it's a function of theta. L stands for the likelihood function. This is also known as the likelihood function. So of course it's a joint density function, so it's going to, the area under that is 1 and it will have, it is what it is going to be, right? So in the absence of anything else, all you could say is this took this particular form because of this data. Otherwise it would have taken some other form. So look at this density function and pick up the most likely value of theta suggested by the data. That's the principle of maximum likelihood. So if you look here, this is the most likely value of the unknown theta suggested by the data. By the data that you just collected. So we will, we can call that to be theta hat ml. So again, you can see from the diagram, in some cases you may have, it could be like this. So you may have two solutions which are, you could have multiple solutions. It could, if it is unimodular and nice and one peak dominates, then the theta hat ml will be unique. Otherwise it could be conceivable that you can have multiple solutions because here both are equally likely. So it can have multiple solutions. And in general, I mean pictorially of course I can write it like this. In general it may be, this may turn out to be a non-linear problem as I am going to show you, etc. So, but if it is, if the density function is smooth, then you can find the maximum likelihood by simply taking the likelihood function and taking the derivative with respect to theta. So you could do this, right, of the density function of R and theta equal to 0. Or sometimes it is easier to work with the logarithm of the density function. So you do either do that or you do this. So to quickly, so let me do a few examples. As I said, this has got some remarkable properties, the maximum likelihood, as we will see. So none of the previous things would work, but this is a general principle. So sometimes this is also, as I said, written simply like this. And we put a subscript r to remind that it is of course a function of r, but the unknown here is theta, L of theta, likelihood function. So if the data xi, let's say xi or ri are Gaussian, and let's say the mean is unknown, and you have, they are all independent, identically distributed, then the joint density function of x1, etc., xn is the product of the density functions fxi. And using our notation, we will say that it's also a function of mu. And variance is 1, so this is 2 pi sigma squared is 1. Because of the product, you get n of them, e raised to minus sigma xi minus mu the whole squared over 2. So according to the principle of maximum likelihood, you take the derivative with respect to mu. We know this is unimodular, so we can also do the logarithm of f. So that will turn out to be minus log 2 pi to the power n by 2 minus sigma and so if you take the logarithm with, the derivative with respect to mu, there is derivative with respect to mu, the first term goes away. The second term you get minus minus, so sigma xi minus mu I equal to 1 through n equal to 0. So you get n mu or mu hat maximum likelihood is sigma xi I equal to 1 through n. So this is a very classic result. If you have a joined, if you have Gaussian data and if the mean is unknown, the standard operation that we do, take the data and add it up and divide by n, which is the classic sample mean, right? Sample mean is the maximum likelihood estimate. That's the theorem now, right? And similarly, you can find the estimator for this variance also. Assume mean is known and the variance is unknown. So if the same problem, so let's say the variance is sigma squared, and I'm going to, so we have done this, so let's do it this way. So there will be a sigma squared here, sigma squared here, this will be sigma squared, there will be sigma squared here, right? And I'm going to take the derivative with respect to sigma squared. Remember, sigma squared is the unknown. Sometime maybe next week I could talk about the maximum or finding an estimator for sigma. That's a much harder problem. So this is not like high school where you say, okay, if I know about sigma squared, I should know about sigma. That's finding an estimator for sigma is, you cannot get it from knowing sigma. This is where the course becomes, has its own life, right? Anyway, let's just do the, so this is the classic estimate, as he said, sample mean. So now if you take the derivative with respect to sigma squared, do you remember this term also turns out to be important, right? And what is it? What's the derivative? Oh, so let's rewrite this term. This was minus n by 2 log 2 pi plus log sigma squared, right? Right? Log this is, so if I take the derivative with respect to sigma squared, remember, think of sigma squared as one variable y. So anybody, what's the what derivative of 1 over sigma squared with minus n by 2 sigma squared, right? And here you get what? Anyone? So these are all constants, so that stays like this. So this becomes what? 2 sigma squared, that's 1 over sigma squared. So sigma squared squared minus 1. What is the derivative of 1 over x? Minus 1 over x squared, isn't it? dy dx. So that's what I wrote there. So let's simplify and see whether, what do we get? So 1 over sigma, this equated to 0. So you get sigma squared ml. Yes? Sigma squared cancels, then you have 1 sigma squared, 2 cancels, this n goes, so you get this. So that's also, this is an estimator, right? Now the third case is, you can clearly, you have a question? Third case is what? Both are unknown. Then you do the derivative, what we did both. You have 2 unknowns, so you have, take the derivative with respect to mu, derivative with respect to sigma squared. You can see the first equation is going to give you exactly what we had. Second equation is going to give you this, but this is unknown. This should be, the solution should be, this should be ml. So then this is going to be 1 over n. xi minus x bar summation I equal to 1 through n. So that's going to be the maximum likelihood estimator. If the mean is, so we have 3 problems. Remember, I just sort of did it. One is mean is unknown, sigma squared is known. Then sample mean is the optimum, maximum likelihood. Second problem is mean is known, variance is unknown. Then xi minus mu the whole squared, the sample variance is the optimum because mean is known. The third thing is both mean and variance are unknown. So you have two differentials and you all it says is replace the mean by its a sample mean. Now you may say that looks obvious. It may be obvious, but that's the optimum. Yes? You have...
I'm still not sure why setting mu to above.
Yeah, remember you have two derivatives, right? Mm-hmm. And the first case, this will easily go through. This you will get this to be x hat, right? Okay. Second one you will get with this unknown, right? But this, remember the two equations are equal to 0, mu equal to mu hat ml. So it's a coupled set of equations. Fortunately here we are, the first equation we can solve for this separately. In the second equation you just substitute it here, then you get this. Now let me show you a case where things are not this easy. So suppose the data is x is gamma, x or r is gamma, with the parameters alpha, beta, both are unknown. So you have the joint density function of I think this is what it is, right? So that's the joint density function of I'm just considering just one parameter. And if you have not R, yeah, okay, so I wrote it as X. So let's say these are Xi, and it is I. We can even consider so your likelihood function of all the X is going to be of alpha, beta is the product of the joint density function, assuming that this data is independent. So this is going to be beta to the power n alpha, product of xi alpha minus 1 e raised to minus summation beta xi over alpha n, right? So now I'm going to take the logarithm and before that, let me just make sure I wrote the density function correctly. Anybody has those notes? I brought everything that I didn't need. If you, yeah, anyway, I think this is good. Yeah, I did upload some notes there. Did you see it's called parameter estimation or not? Anyway, you could check under resources, under notes or something. I have all these notes, a set of notes. And if you open it up, look at what is the density function for this jointly. You see something called parameter estimation. Open it up. Is this right? The third page or something? Second page, third page. The joint density function for gamma. This is alpha minus 1. That's what I'm doing. Then everything is good, I think. No? All right, so let's take the logarithm of the likelihood function. So that's going to be n alpha multiplied by beta, log beta. Look at here, plus alpha minus 1 logarithm of pi minus beta xi, sigma xi, minus logarithm of gamma alpha, okay. Now, look how complicated this comes. Both alpha and beta are unknown. So I'm going to take the derivative of this with respect to alpha, and I'm also going to take the derivative of L with respect to beta and solve two equations simultaneously. So what is it? The derivative with respect to alpha is n log beta. Then plus log of pi xi. Derivative with, so this is partial derivative. There is nothing here, and this is going to be minus n gamma prime alpha over gamma alpha equal to 0. Okay. Yes? See, the last term is 1 over gamma alpha, and the derivative of this with respect to alpha, I just wrote it like that. So this, of course, you can write it as sigma log xi. So now let's do the derivative of logarithm of the likelihood function with respect to beta. So that's n alpha over beta. There's nothing here, and here is going to be minus sigma xi I equal to 1 through n equal to 0. So either way, if I solve for beta, so beta hat ml is going to be from here Is that right? Did I do it right? So because it's, so this equation goes here. I bring this down and this goes up. So beta hat ml is n sigma xi. N I take it down as 1 over n. Then this becomes alpha hat ml over x bar. Yes? This is correct, right? And but the problem is alpha hat ml is known. So I can take this beta hat and plug it in here and then solve for alpha. And you can see alpha is a highly nonlinear equation. So if I take this and substitute it here, so this is 1, this is 2. If you substitute 3 into 1, you get n log beta. So that's n log alpha minus log of sigma xi. So n log alpha minus n log xi. And here is, so this is becoming n log alpha minus n minus 1 log n log beta. Beta is this, so n log alpha minus n log x bar. I think that's all you can do. Plus log sigma log xi. This is, here the summation is inside, here the summation is outside. Minus n log n gamma prime alpha over gamma alpha. This you need to equate it to 0 and solve for alpha. This is highly nonlinear. because of this gamma functions and alphas, etc. So you can of course do numerically, or once you know these values, you can employ some numerical techniques to complete. You get, so this gives us alpha hat ml, and then you substitute it here, you will get both of them. So what is my point? My point is the maximum likelihood estimator could be messy. Now let me stop this with one more final example, and which we will be using from time to time, is when all the data is uniform. So suppose the xi's or ri's are uniform in 0 to theta. Remember, theta is unknown. I equal to 1 through n. So the problem is, next example is the data is uniform somewhere from 0 to theta, but we do not know the theta. So this is like a discrete version of this is the taxi problem, right? So in New York City, for example, there are, assuming each taxi has some serial number which is serially written one as the taxis come out of the, go into the operation. So somewhere 1, 2, 3, etc. up to some n. That n is unknown. So you make some observations. So you stand somewhere and you can read a taxi number. So you make a few observations, then we want to get an estimate about this theta, because every number is going to be between 0 and theta. So that's the discrete version. I'll come to that also. But let me finish this up. So the density function of Ri is like this. So f R1 etc. Rn given theta is the product of f Ri. So this is of course 1 over theta, I equal to 1 to n. So this is 1 over theta n. But you can see this is xi, right, or Ri. So that means R1 is between 0 and theta, R2 is between 0 and theta, etc. Rn is between 0 and theta. So how will you express all these conditions together? Anybody? So R1, all of them are less than theta. R1 is less than theta, R2 is less than theta, Rn is less than theta. So that's the same as. So their maximum of R1, R2, etc. Rn is also less than or equal to theta. Yeah, and the minimum is also greater than 0, right? So you can replace this 2 by 2 conditions. So if you want, you can use an you can use an I function, an indicator function, right? Saying maximum of Ri comma theta. So from theta is beyond that, and here theta is. So from here, remember again, the likelihood function is a function of, as a function of theta. If you plot, look at here. This is your likelihood function. The likelihood function says, what does it say here? Theta, this is valid for theta. This is the minimum has to be greater than 0, which means all of them are positive. But the condition on theta is what? This density. This is the density function provided theta is greater than max. So you can see that this is the. Then it goes down as 1 over theta n, right? So this value is your max of R1, etc. Rn. So the principle of maximum likelihood says, take the maximum value for theta which is suggested by the data. So what's the maximum value of theta here? Anyone, what's the maximum likelihood estimate here? Huh? Max itself is the maximum likelihood. So in this problem, the maximum likelihood estimator for theta is a max of R1, R2, etc. Rn. So that's a random variable, and that's a nonlinear function. It's not a linear. So I went through all this couple of cases now, right? In the Gaussian case, sample mean was linear function. The unknown variance was quadratic function. Then the
Can you explain the indicator function of the last?
yeah, I'll come to this. So we don't really need the indicator function here. Indicator function is to say that so here the indicator here. It's like say, just putting this, when theta is greater than this, the indicator function is 1.
Yeah.
And so this says that if the theta is greater than this, so from here, this is the key diagram. Because the likelihood function goes like this, the value where the theta, where the function peaks is for this value. Right? Because look here, theta is, that the density function is only valid if theta is greater than this. That means this density function, of course theta n goes like this, right? It's and so the largest value for this function is when theta hits this. So that must be the maximum likelihood estimator.